Max Planck observed that energy for this photon process can be gained or lost only in small number multiples of h times nu, where h is Planck's constant, and that's a value of 6.62 times 10 to the minus 34 joules. And nu is the frequency. So the frequency is going to be related to the energy. So here's our connection between energy and frequency. So frequency and energy are directly proportional. The higher the frequency, the higher the energy, the bluer the light, the shorter the wavelength. The change in energy of a system, delta E, can be represented by the equation delta E is equal to n times h nu, where n is some integer, 1, 2, 3, 4, 5, and h is Planck's constant, and v represents the frequency of electromagnetic radiation. So this integer here, n, exists as 1, 2, 3, 4, some sort of whole number, some sort of quantum number, right? So quantum just means that it's acting in kind of discrete intervals. So this is the start of our quantum theory. So 1900, Max Planck gets the idea that radiant energy could only be emitted or absorbed in discrete quantities. And he called these quantum or packets of energy. And he correlated data from a blackbody experiment to his quantum theory. And this totally revolutionized the way we thought about how light and energy work. It made it discrete and no longer continuous. Right? So continuous means there's an infinite variety or an infinite resolution to how far and how small those changes in the amount of energy would be for a given photon compared to another one. So continuous means that, yeah, there's discrete numbers. It goes up in chunks of energy. And this proves that energy does have particulate properties. So this is one of the steps that helped prove that light is acting like a particle because it's acting in discrete chunks. And really what he was doing was helping to address what's called the ultraviolet crisis. So if you look at classical theory predicts that as you get something up to about a temperature of 5,000 Kelvin, the photons that it put out are going to be exponentially increasing, right? So you're not going to get infinite energy out once you heat something to 5,000 Kelvin. So we had data that shows, okay, here's 3,000 Kelvin, right? And this is showing our wavelength and the intensity at each wavelength. And so as you heat something up, it's going to go from red hot, and then you're going to pull in some more stuff in the blue end of the spectrum, and you're getting some red and some blue and some yellow, and so now it's getting white hot, and then you're putting in a little bit more, right, eventually. So you've got different temperatures giving you different colors coming from this black body. So you got a different peak here that's following something called Wien's law, where this peak is located. But if you follow the classical model, at 5,000 K, you would have shot up all the way up exponentially. And obviously that's not what happened, right? You're not getting infinite amount of energy out of somebody, working a forge at 5,000 K. So the reason why this is called black body is because a black body, which is sometimes called a cavity radiator, that's because you would take something like a furnace and you would poke a little hole in it and you look at the energy that was coming out of it. So you make peepholes into a furnace, a good source for black body radiation. And so if you think about like a temperature profile when you talk about cold versus warm lamps, right? So you can also put a temperature profile here relating the temperature in Kelvin to the perceived temperature of a lamp. So Planck's theory says energy of a single quantum of energy is equal to h times nu. So E is the energy in joules, h is Planck's constant, and nu is the frequency. So this is going to tie together our frequency of light, which is related to the wavelength, and the energy of that light. So let's do an example. If you take blue, color in fireworks, that's coming from copper 1 chloride to about 1200 degrees C, and then the compound emits blue light having a wavelength of 450 nanometers. What is the increment of energy? So how much energy is in that photon emitted at 4.5 times 10 to the 2 nanometers? So the quantum of energy is going to be calculated from delta E is equal to h times nu, we've got a wavelength here. Can we convert that into a frequency? Yes, yes we can. Can we then convert our frequency into an energy using Planck's constant? Yes, we're going to do that. Okay, so the frequency in this case, we're going to calculate using nu is equal to c over lambda. So we'll do 3 times 10 to the 8th meters per second, that's our speed of light, divided by 4.5 times 10 to the minus 7 meters, that is our wavelength. So here another pro tip, if you make this guy nanometers and like our visible light in scientific notation, it's roughly 400 to 800 nanometers, so you're going to get like 4.00 times 10 to the minus 7 meters. Right? So if you want to convert your couple hundreds of nanometers into meters, it's going to be times 10 to the minus 7 meters. And that gives us 666 times 10 to the 14 hertz. Right? Again, 14, that's roughly our order of magnitude we'd expect for a visible photon. Next, once we've got this, we're going to plug it into our equation for the energy. So our energy is equal to h times nu. So take our Planck's constant, 6.6 times 10 to the minus 34, multiply it by this number we just got here, 6.6 times 10 to the 14th per second. Our seconds cancel out. We end up with 4.4 times 10 to the minus 19 joules. And this is a good order of magnitude for the energy of a photon, minus 19, minus 18 for a visible photon. So a sample of copper chloride emitting light at 450 nanometers can lose energy only in increments of 4.4 times 10 to the minus 19 joules, the size of the quantum in this case. Electromagnetic radiation is a stream of particles with discrete energy, and we're going to call those guys photons. The energy of each photon is going to be expressed by h nu, so we could say the energy of a photon is equal to h nu, which is also equal to h times c over lambda, where h is Planck's constant, nu is the radiation frequency, and lambda is the radiation wavelength. So we've known for a while that light acts like a wave, right? And now we've got Planck coming in saying light, well, it's only acting in discrete intervals. When you get down to really small amounts, it's going in this kind of quantized way, and that's kind of like a particle, right? Why would a wave not be able to have a continuous range of values, right? And so what happened next was Einstein's discovery of the photoelectric effect, or description of the photoelectric effect. And so if you take a vacuum tube, right, and you've got a voltage that you apply between an anode and a cathode, right, so you get some voltage source here, a potential. No current is going to flow, right, because there's nothing to really connect that circuit and complete the circuit. But if you have an incoming photon, it can knock off an electron from here, from this surface, and then it's able to go to this cathode, right? And if I've got a movement of charge from one space to another, I've completed the circuit and current starts to flow. Right? So electrons, which are ejected from this metal surface, only are going to generate a current when light is of a certain frequency. So, for example, if you put red light in, nothing's going to happen, right? And then if you put in blue light, all of a sudden it works. Even though the light has the same photon flux, right, the same brightness, the frequency matters. So Einstein proposed that particles of light are really photons, which are going to act like packets of light energy, and deduced that the energy of a photon is equal to h nu. And so this is what he got his Nobel Prize for, not E equals mc squared, but for the photoelectric effect. So only when light with a frequency of photons such that h nu is equal to the energy that binds the electrons to the metal is sufficiently energetic to eject the photons. So if you come in with red light, like some weak, low energy red light, nothing might happen. But if it comes in and it's green light that has enough energy to kind of kick that photon off, kick that electron off, the energy is sufficient to release that electron, then current starts to flow. And if you come in with blue light, which is even higher energy, right, it's still going to kick those electrons off. If light of a higher frequency is used, the electrons will be ejected and will leave the metal with additional kinetic energy. And so what's the relationship between energy and frequency? Higher energy, higher frequency. Light of at least that threshold frequency of any end of greater intensity will eject more electrons. So if you throw in more photons, a greater number of photons at the same frequency, you're going to get more electrons out. So here you've got this, here's a graph showing that effect. So you take this irradiation of a clean metal surface with light causes those electrons to be ejected from the metal. Therefore, the frequency of the light used for the radiation must be above some threshold value, which is different for every metal. And so we're going to see nothing happen. So here we've got low energy to high energy. So red light to blue light. So red, orange, yellow, nothing. Green, oh, it starts to turn on. Right? And anything higher than that green would allow you to get through. Right? If you throw in and make that green light brighter, you're going to get more intense light. You're going to get more current out. Increasing the intensity of the light while keeping the frequency constant increases the number of ejected electrons, but it doesn't change that threshold value. So what this is saying is that this is like acting like a ballistic particle, where it's actually physically knocking one of these electrons off of that metal surface. And that would not happen if light was just acting like a wave. Right? So the minimum energy required to move an electron is going to be what we call E0, where E is equal to H, or E is equal to H times nu zero. And when your frequency of light is bigger than nu zero, the excess energy that is required to remove the electron is given into it as kinetic energy. Right? So the kinetic energy of that electron, you're going to do 1/2 mv squared. Right? So this one is a v. And so that's going to be the difference between our h nu and our h nu sub zero, where m is the mass of the electron, v is the velocity, nu is the energy incident on the photon, and nu sub naught is the energy required to expel the electron. So now we've got two different lines of evidence. Right? There's a dilemma caused here. One is light going to act as a wave. Right? So all of our previous two-slit experiments, we've known for quite some time that light's going to act like a wave, but now you've got Planck and Einstein coming in, and they're like, well, light's kind of acting like a particle. Right? So is light a particle or is light a wave? And the conclusion is that light must have particle characteristics as well as wave characteristics. So this is a case where you can have your cake and eat it too. Now on to our Bohr theory. So Niels Bohr proposed in 1914 a model of the hydrogen atom as a nucleus with an electron circling around it. This is sometimes called the planetary theory, or the planetary model. In this model, the energy levels of the orbits are quantized so that only certain specific orbits corresponding to certain specific energies for the electron are available. So you've got one nucleus that's like the sun, and then you've got an electron orbiting around it, much like a planet orbits around the sun. Right? So our electrons are going to be like our planets. Our nucleus is going to be like the sun. Right? It's got most of the mass, just like the sun has most of the mass in our solar system. And then we got these electrons kind of going around here on these discrete energy levels. Right? So if you go from one orbit to another, it's different energy. Right? So only specific orbits are allowable. When an electron falls from a higher energy orbit to a lower energy inner orbit, it's going to give off that energy, and it's going to give off that energy in the form of a photon. And that frequency, that energy of the photon, is going to correspond to the frequency of the light that is emitted. So Planck's theory, along with Einstein's ideas, not only explained the photoelectric effect, but it also made possible for scientists to unravel the idea of atomic line spectrum. So here's Bohr, and he is Danish and died in 1962, so not that far away. He actually worked with J.J. Thomson.